Hello there. In this video, we are going to cover the stack data structure in Java for the UILCS written exam. So first off, what is a stack? A stack is a data structure where elements are added to the top of the stack and conversely removed from the top as well. The best example for a stack I could think of is a stack of books. Let's say here I have a stack of books. But I have like 5 books in my stack. 1, 2, 3, 4, 5. And I tried doing a 3D view that looks chopped. Let's just do a 2D view instead. One book, another book, like this, right? So we have a stack of books. Let's think about the principles behind what does it mean when you add to the top and remove from the top. Well, if I want to add a book, let's say this new book that I really liked and I want to add it to my book or stack of books. Would you really add to the bottom or where would you add it, right? We wouldn't add it to the bottom because that'd be cumbersome. We'd have to lift up all these books just to place this book here and stuff. And conversely, that's the same argument why I wouldn't add it anywhere. Sorry, conversely, the same argument why I wouldn't add it anywhere like right here or right here because you still have to lift up books, you still have to do manual labor. Typically, when we have a book and want to add it to this book pile, you'd add it to the top, right? So you'd add it right here. So this is what it means when I say a stack data structure as the top. It's synonymous to what we just did here. But we're adding this book, which you can use an element, right? And we're adding it to the top of our stack. Okay, cool. So hopefully this makes more sense now. And now let's think of what it means when you remove from the top. Well, let's say you want the whole philosophy behind the stack data structure is you're supposed to, if you want to access this bottom element, remove all the top elements and then you'll be able to access it, right? And this comes from a real life version of the stack because if you want to access, let's say we want to read the book at the bottom of the stack, well, if we pull out this book, all of our other books are just going to fall on the floor and create a huge mess, right? So what do we actually do? Well, we remove the book at the top and then we put that in a separate pile. So I'll visualize this a little bit better. We take that book, if we like remove it. We take the next book, which is our new top in a way, remove it. Take this next book, remove it. Take this next book, remove it. Take the next book and remove it. And then lastly, we have this book, right? And what do we do there? We essentially just remove the top of our stack each time, right? Put this all back. When we remove that, now this would be our new top. And what do we do? We removed that. And then this is our new top. And what do we do? We removed that. And then this was our new top. And what did we do? We removed that. This is our new top. We removed that. And then now we're down to the element we wanted. This is how a stack should work. So, in order to do this, Java of course has methods. The first method is the push method, which will take in your data. Or I guess I'll actually call this your element because will stay tuned with what we've been discussing with your element, right? What this does is really simple. This just pushes the item to the top of the stack, right? If we have a stack of books, we can say this element is now going to be pushed here to the top, right? It just takes the element, puts it at the top of our stack. I actually think that visual example is helpful. A lot better than me writing it out in words and you having to imagine it for yourself. Pop, which takes in no parameters, removes the element at the top. So, and returns it. So let's say this was our array. Let's say we pushed it like this. We would probably take this element here. And that'd be the element we return. The pop method essentially would take our stack and make it look something like this. Returning element. So this is the pop method. You can see this is our original one. Then we ran the pop method and you can see that the element at the top of the element at the top of our stack got removed and was returned. That's all the pop does. It takes the element at the top of your stack, takes it off the stack and returns it. Now conversely, let's say we just want to see what the element at the top of our stack is. We don't necessarily want to remove it. So the next method is the peek method. 1, 2, 3, 4. Let's say we have this is our top element again. Well, all peek would do is if this is our top element and we were to call peek, then nothing would change really. We would just to that last element, we would just return it. But do you notice a difference with pop and peek? When we did pop, our stack looked like this now, and we just had returning this. When we did peek, our stack is still the same. Okay, my articles are kind of bad, but so they're still the same, and we're just returning that element still. We're not removing it from the stack, it's still there. Okay, so the next method is the empty method. And this one I can just write out. So this will return as two cases, it'll return true if true when stack empty, or there's no element on a stack. So return false when we have at least one element on our stack. I mean, I think empty is pretty easy to understand. It's in the name when our stack is empty. Okay, cool. Ooh, kind of weird. Let's just take this stuff. Okay, cool. And I also noticed I forgot to add return types. So this will actually return when you're pushing the element, but push it'll also push it like here as you saw, and it'll return the element. With pop, again, we saw it'll return the element it takes off the stack. Peek will also return the element at the top of the stack. Empty will return a boolean, right? True or false, as we wrote. And then the last stack specific method is search. And search is weird, so we're going to use a visual diagram example to help us. Let's say I'm looking for an item. So search basically takes in T data and it'll search for in the stack. It's in the name though. Let's use an example to help us understand this. I'll do search. Let's say I'll search for the number 2 and a stack of numbers. So a stack of numbers looks like this. 0, 1, 2, 3. So we're searching for the element that has the data 2, which is right here. And what the search is going to do is similar to index of. It's going to return the index at that location. So what's the search function? How does it work? Well, search is first of all, it's index or one based. So one based indexing. So you can use this as index 1, index 2, index 3, index 4. And you also saw it starts at the top is your index 1 and your bottom is index 4. Alright, so it just goes top to bottom, right? Those are the two major components of the search. From there, everything else is pretty similar for indexing. You're gonna go here, not it, there, not it. Okay, 2, boom, 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 that's it. What index is that? That's tree, right? So we'll return tree. Just say this whole thing returns tree. So these are the 5 major functions that are stack specific. Now, why do I say stack specific? Because the stack actually implements the vector interface, and that's a problem. See, stack was actually made a very, very, very long time ago. One of the earlier versions, very early versions of Java. And the thing is, when it was made, we had the vector interface and everything seemed good. But the vector interface actually has methods that defies the purpose of a stack. I said that a stack is supposed to be a uh what we call this a first in we call this a last in first out sorting algorithm, or sorry, not sorting algorithm, data structure. Sorry, we call this a last in first out data structure because think about it. When we're thinking about it, right? The last element that we add to the stack, or we push to the stack, is also the first element that gets removed, right? Because whenever we push that element to the top of our stack. Whenever we pop from the top of the stack. So the last or most recently added element is also the first element that gets removed. Last in, first out. And I also said the whole nature of a stack is that you're not able to just willy-nilly just add at some index, right? You can't add at some index. Well, really, if we're talking about it with the vector, you can't add an element at a certain index. That's not allowed. Nor could you like get the element itself from an index. You can search for the index of an element, but you shouldn't be able to get it, right? Because how do we define, and also neither should you be able to remove an element from a certain index. We said a stack in our first example, if you want, should only work by removing things from the top or adding things to the top, right? Because if we think about it, in our books example, we said how you can't just add an if this is index 0, 1, 2, 3. If you want to add a book, we'd add it to the top of our stack, right? Not in the middle or anywhere else because you'd have to lift up books and put it in there. Conversely, that's why we can't just remove any index because we said if we were to try and pull this out, this book would fall and it would create a mess, right? And that's why we'd have to remove all of this, or we'd have to remove this, and then we could be able to get this, right? Remove the books that come on top, right? This is how a stack is supposed to be done. But there's these methods in the vector interface, add, where you pass in a t element and your int index, get, where you pass in int index, remove, which is your t element and index. Define these, because with add, it'll take in the element and add it whatever index you want. With get, it'll just let you just access whatever book you want from any index. And with remove, it'll just remove any book from any index too. This completely defies what we said a stack should be able to do. However, when we're creating a stack, they created it with the vector interface. So a stack has the add method, it has the remove method, it has the element, it has a bunch of stuff from the vector interface, and if you want, you can look into it more on your own time, more focus on stack specifically. And because, actually no, let's go back to a little bit. We'll talk about some vector interface methods because I think you should understand them, right? We get methods like element. Actually, no, let's not discuss. We're going too much detail about this. Right, so it's basically essentially going to add in all of these vector methods from the vector interface that define the nature of a stack, right? So even though we could, even in a stack, yeah, that's what I want to bring up. Maybe saying, say, okay, then what's the whole point of a stack? Or they're just being dumb or something? Like, should we not use the stack, right? So why even use a stack? Well, actually, that's a good question because Java doesn't want to use a stack anymore. How we're talking about stack because UILCS will test you on it, but Java does not want you to use a stack. Java would like you to use the array deck, but that's as far as I'm going to bring up about the subject because in terms of UILCS content, you don't need to know what an array deck is. If you want more information on decks and such, you can actually watch our linked list video. Or it's my, I don't care, why am I saying our? It's only me here, bro. It's just me. Okay, anyways. So, we understand how the stack works. We understand the main method of a stack. Let's code one. Here we're back in the data structures class. That was the linked list. If you want, you can also watch a linked list video. I actually recommend waiting to watch the linked list video until stack queues come out though. Let's add some generics to this. I have a stack, public, stack. I need a capacity. Capacity. So let's create we're gonna make something that's called an array backed stack. Array is gonna handle our internal application for this. I want to reference to the top of the stack. That's important for us to have. And then I also would like to create a T type array. So array is the new object of capacity. This will allow us to store anything in our array. Okay, let's do T capacity. Is that even allowed? No. Okay, here. Then we can just probably do this. Make this an object array too. And this should work because we're only ever allowing one type. Like all of our data is going to be type specific, so even though we're making this an object array, we'll never run into the issue where it will contain more than one type of object. Top equal to 0. Let's start by defining the push method. So public, we said it will return the data push. Let's just run this and we'll say to our array top push add data. And so actually we can make this we'll do 0. So we'll go to our array. Why are we getting a weird line here? We can cast this into an object. We'll have no issues with that. Oh, oops. So that'll handle that and we'll say we'll take the array at 0. Capacity type T. This will work. Let's do public T pop. So let's do R minus. And again, we'll cast this to type T for generics. Public, let's do public boolean empty. We'll return side or top, not top, because if top is equal to 0, then let's do this. Ooh, this is cool. This is an interesting way of looking at it. And we'll just return if top is equal to -1. So what are we actually doing here? I'm saying this is going to be -1, and then we could say if our top is equal to -1, that means we haven't pushed anything. Why is that? Because when we push something, we're incrementing top to become 0, and then we're setting that to our data. And so even here, I can actually just say return top, right? So every time we keep on pushing, we'll increment it to 1, push, and so on and so forth, right? And then lastly, to public, it should be int search. I'm taking t data. I'll change this from data to lm because that's what I wrote when we were talking about it originally. It's just a variable name though, it doesn't mean much. Lm, so what do we say this would work? We'll do a simple for t data in array. It should probably be object array. Check if data dot equals lm, and if true we want to return just index. Now that's some arbitrary value I need to make right now. Int equal to 1, return index. Otherwise, let's just do index plus plus. And so if nothing is found, let's return a negative. Alright, so this is our implementation of the stack data structure. Let's test this. So I'm actually going to call this a SID stack so we can get accepted. So if I don't call it a SID stack, we might actually run into an issue where when I try and actually test this in here, Java will use the actual stack implementation, which we don't want. We want to use our stack. Let's get rid of this. I'll say SID stack of type integer is equal to SID stack. I need a name, so I'll call it a stack. Let's set our capacity to 5. Let's stack dot push 0, stack dot push 1, stack dot push 2. Ooh, I forgot a method. Oh, I'm so silly. I forgot the peak method. Public p. I want to write it after pop. Public p peak. Turn the array at 0. And this should be top, not 0. That's an incorrect statement. And let's cast this. Okay, cool. Stack that push 3. Let's make a int of top is equal to stack dot pop. Let's print out top. So this should be true. We did everything correct. Oh, cool. So if I just let's actually test that a full stack is working by creating a for loop at the integer element stack. And I don't think we could do this directly with stack because this is not. But here, what we could do is okay, that'll require a little bit more complexities than I have in my system. Let's just run this. Let's just run this. Like obviously our stack is missing some stuff. Like we don't have a size. We don't have anything like that right now in my implementation. But it's just the basic one. You can see some of it. It just will house all the functions that we talked about. Stack.pop. And this is not to be interesting. One thing I forgot to do is if we need to add some checks. Like if top is equal to if top is equal to -1, that means we don't have a top, so just return -1. Let's return null. Alright, let's run this and see what we get. So we should get 210 null null. Boom. 210 null null. This tree is coming from this, so if I move this. And then if I try and let's do a little peek, let's peek at the top of our stack. Stack dot not push peek. This should return 2 if everything worked. Okay. And then lastly, let's do stack dot let's print stack dot search for 0, which would be 1 2 3. So it should return 3 if this is correct. 2 1. Well, I know why. I understand it. So this is an incorrect way. Int I will say that's equal to the array at index top. We'll say I is equal to top until I is so as long as I is greater than or equal to 0, I minus, right? And so what this is going to do is we're just going to say if the array at top, the array at I dot equals the lm, return the lm, and then let's actually, no, sorry, not return index, and then let's do index plus plus here. So let's run this now, and boom, we got 3. So I actually want to go over for a minute and explain some of this code. Like in the linked list video, I explained some of the code, so I didn't explain it when I was building the structure. I explained in the linked list video. I explained all the pointer referencing prior, but here I didn't do any of that. So let's actually explain how some of this works. Maybe asking, why aren't you just referencing the 0th element? Shouldn't that be the top? Not really, because remember, right, with the array, whenever you push an element into our array, whenever we add it, let's say add an empty array. When you add an element to array, like 0, it'll go here, right? And when we add the next element, it'll go here. Well, according to our philosophy for the stack, this should be our top and not the 0th element. So the easiest way to do that is by storing that top value. So by storing this index, so whenever we increase our value, as you can see whenever we push something to the top, just have some variable to always look at that index, which is why we have top here and why we're writing it like this. Or this is why whenever we add an element to our stack, we're increasing top by 1, right? Here top would be 0. Then our top is 1. Then our top is 2. That's the hardest thing that's really the hardest thing to understand about the stack. It's just that. I'm not gonna go into the generics because I'm gonna make a video on generics later. Pop, of course we need this check because we don't want to return null accidentally in case our, let's say our stack has no elements, right? If we try and call this, we're actually going to get an array out of bounds error because when our stack has no elements, top is -1. An array of -1 doesn't exist. So we're checking, making sure it doesn't happen by doing this. Peak is quite simple, we're just getting the top element. Empty might be a little bit weird to understand. Top is equal -1. Why is that? Well, when we construct our stack, we give top a value of -1. The only way top is increased is if we push something in the stack, and if our array is empty, we return null. So we don't even run to this case where we could decrement it even further. So really, then all we need to do is see if that top value is still -1, and if it is, good, then we're chilling. We have no elements in our stack. Conversely, you could do if the array dot. Actually, you can't really do that. No, you can't, because we're not actually removing anything from a stack, right? If you look at the top value or the pop, we're never removing the element. It's actually an issue. We should do that. Ooh, big catch hides type. So let's just set array at top equal to null. And I'll take you and I'll store you in some new reference variable. Actually, no, this should be fine. This is fine. Because even, yeah, so here, right, this still is technically shrinking our size of our stack. Okay, so yeah, right? So if you think about it, our top is only -1 when our stack is quote unquote empty. Our stack isn't really being empty. We still have the full array of our elements. Just the only thing about this is, yeah, the only thing really about this is just the fact that, no, sorry. So our top is -1 and our stack is empty, right? When this is -1, our stack never actually becomes empty. What's actually happening with this top is, even if we have an array, this is the kind of beauty about this, even if we have an array full of elements, right? If we say that if we're looking at our top is kind of just a pointer variable, or a ref here, okay. I think one thing that might be confusing is we're not removing anything from the top, right? We don't need to remove anything because just by decrementing top itself, we are limiting our range of what we're really looking at, right? Even though an array will contain this, as far as the stack is concerned, the stack looks like this now, right? 1, 0, because our top is here. So simply just by moving the top variable, we can really control our stack around. And don't worry, if we won't really go over capacity because remember, let's say we push to 0 and we moved every element until we had 0 elements left, then our top would be 0, and so this would just simply override these elements with the new ones we want. Well, it's quite the simple array stuff. This is also straightforward. We're doing a reverse for loop. Starting at the top, going to 0. If we're equal to the element, return that, and then return that index, and we're starting our index at 1 for the one index. One index or one based indexing that I discussed earlier. The last thing we need to talk about is the time/space complexity. So /space complexity. So the stack itself, or well here, all the operations in stack have a time of 01, and they have a space of 01. Space. The only one that doesn't have a time of 01 is with the exception of search. That has a time of 01. And this also has a space of 01 because we're looking at every single element. So search. But then also the stack itself in memory has a space of 01, or of ON, sorry, because it's a full array list. Okay. And yeah, so thank you for watching this video about the stack data structure. External time and space complexities. Of course, I'll do a video like I did with sorting at the very end, going over all the time plus space complexities for all the various data structures and algorithms. But that's going to be it for stack.